Right, now that we've talked about collision theory and the temperature dependence of K, let's talk about some of the calculations we'll associate with it. And we're going to use the Arrhenius equation, which is this representation of K that we've already introduced, that it's equal to that frequency factor times the exponential factor that includes the activation energy. Um, and so we have two different ways that we can approach calculating K. Or the activation energy, kind of depending what the problem is asking. We have a graphical approach and we have a 2-point approach. And typically we're using reaction rate information and a K value to find out what the activation energy of a reaction is, so we can better understand it. Um, so let's talk through the graphical approach first, then the 2-point approach. So if we have the Arrhenius equation, it looks like a complicated thing to deal with graphically. So if we take the natural log of the entire equation, though, then we can rearrange this into an mx plus b style format where we have y, that is the natural log of k. We have mx here, where x is going to be 1 over t, and our slope is going to be negative activation energy divided by r, and our b is going to be the natural log of a. So if we go ahead and we take our y versus our x right here, and we plot the natural log of the rate constant versus the inverse of temperature, then we'll hopefully get a straight line. So we'll get a straight line, and that slope is going to be the activation energy, and the y-intercept is going to be our frequency factor, which is really useful. So anytime we have something that's two lines, we can always just take 2 points and find out what the slope is, or the rest of the information in the line from those 2 points, because 2 points make a line. And when we do that, we can create this 2-point approach that is going to be the natural log of the 2 Ks that are being compared is equal to the activation energy divided by R times the difference between the two inverse temperatures. So this is starting to look a little bit like the Clausian-Clapeyron equation, which we saw earlier in the quarter. So here is an example of an equation where we took some information about the rate constant and how it changed with temperature. So that meant experimentally, we ran the the reaction several times at different temperatures and calculated the rate constant for each one. And so that way we could correlate the two pieces of information and then plotted the natural log of that rate constant versus the inverse of temperature. We got a line like this. And then you can fit a line to the data points and pull a trend line out of it, which was done right here. And then that gives us a slope right here that we can then set equal to that negative activation energy divided by R. Remember, R is going to be that 8.3145 joules per mole Kelvin. And so solving this equation right here, we get an activation energy that's equal to 4.33 joules per mole. We can also use this line to figure out where the y-intercept is. That's going to be this right here. And so that's going to be our frequency factor, that negative 6.908. And so we can get a lot of information just from graphing this. And here's the same equation. This is looking at, or sorry, not the same equation. Here's another example using the 2-point method. So here we have methane and sulfur forming carbon sulfide and hydrogen sulfide. And we are going to run the reaction at 2 different temperatures. So it was at 550 degrees Celsius, which is 823 Kelvin. And then we also, which gave us a rate constant of 1.1. And then at 898 Kelvin, we got a rate constant of 6.4. And that's inverse moles, inverse seconds, or inverse molarity, inverse seconds, sorry. So this information can be applied in our equation that uses the 2-point method. So I'm going to take that second K and start with that on top. And so that's going to be right here, that's 6.4. And the corresponding temperature will be the first temperature in my equation right here. I'm going to make sure I'm always using Kelvin, so that way I'm not accidentally putting myself in a position where I have 1 over 0 degrees Celsius and something that I can't actually solve because it'll be undefined. So it's going to be K, the higher temperature, or K, over the first temperature or lower temperature K. So I've got that 1.1 K on the bottom, and I have that 823 Kelvin as the second temperature marker. I put in then my R value, and now I have an equation where I can solve for the activation energy right here. And that's what I do. So I rearrange this equation and I solve for an activation energy that's 1.4 times 10 to the fifth joules per mole. And with this type of equation, typically just inputting in the data is the easy step, but then actually getting something out of your calculator that makes sense is the harder step. It might take a little bit of practice. Here's another example with the 2-point method, since this will probably be what you do a little bit more. Um, So here we have, given that K at 25 degrees Celsius is 4.61 times 10 to the negative 1. And then at 50 degrees Celsius, it's 4.64 times 10 to the negative 1. What's the activation energy for the reaction? So for this equation, to solve for that activation energy, I'm going to use the equation, the natural log of my K2 divided by my K1 is equal to the negative of my activation energy over R times 1 over T2 minus 1 over T1. All right, so I know I need to get those temperatures into Kelvin first and foremost. That 50 degrees Celsius, I just add 273. It's going to be 323 Kelvin. And 25 degrees Celsius is going to be 298 Kelvin. So I'll use those values instead of the degrees Celsius. So I'll plug in, and then I'm going to try to solve this on my calculator. So I'm going to be looking at something that's the natural log, and I'm going to start with the higher temperature K value. So that 4.64 times 10 to the negative 1, and then divided by the lower temperature K value, 4.61 times 10 to the negative 1 is equal to the negative of our activation energy divided by 8.314. And then 1 over my higher temperature, the 323, minus my lower, 298. All right, and then I'll be plugging that all into my calculator, which will take a bit. And so when you're doing this, I typically plug in this value here first and this value here first, just so I've got something I can backtrack to if I need to double check myself. And so let's do that really quick. So I could then rewrite this. So I plug these into my calculator as natural log of 1.0065 is equal to negative EA divided by 8.314 times negative 0.0002597. So double check if you're getting to that point, same as me. Then when I rearrange this, what I'm going to do is I'll have my natural log of my 1.0065 times, so it'll be like this, times my 8.314. I'm going to make that negative 8.314. And then divided by my negative 0.0002597. And that should give me my activation energy, which when I calculate it, I get a value of 208 joules per mole. And I have this example also on the following slide too, typed up as well, a little bit neater.